Tonight, it's a real pleasure to welcome Dr. Holly Buck, and she's going to discuss the possibilities of climate engineering as approaches to limiting or reversing climate impacts. She's been very helpful to us already. She attended a workshop helping us get ready the story for Pacific Visions about energy, because there are three components of that big story: energy, food, and water, and Holly was very helpful on the energy side. She grew up in Maryland, got her bachelor's degree from the University of Maryland, Baltimore County. She completed a master's degree in human ecology at Lund University in Sweden, and got her PhD in environmental sociology and emerging technologies at Cornell University in upstate New York, in Ithaca, New York. Prior to her academic life, she worked as a foreign affairs analyst, a geospatial technician for a remote sensing company, and she taught creative writing. She actually majored in English as an undergraduate, and now she's a NatureNet postdoctoral fellow at UCLA's Institute for the Environment. She has a very important book on geoengineering. It's in press, and it will come out sometime in next year, and it's a very important book, and she's going to tell you why we need to do geoengineering in combination with reducing the emissions of greenhouse gases. Please welcome Holly Buck.
Hi, I'm really excited to be here today. And I'm just going to jump right into sea level rise, actually. So you might already know that even if countries meet the pledges they made in the Paris Agreement in 2015, even those pledges commit us to about 3 degrees Celsius of warming. So nations are going to try to get that down to 2 degrees or 1.5, which is what the target they agreed upon. But we're not there yet. And the last time the temperature was that high was 3 million years ago. So you can see kind of what the lock-in sea level rise for 3 degrees looks like here versus 1.5, which is the target. So still some areas underwater around here, but not as bad as 3. We're not even necessarily on track to meet that 3 degrees now. When is this a snapshot of? Isn't this really far in the future? Yeah, this is a couple hundred years at least, maybe 1,000. But any guess to what year this might be? This is a map of Long Beach here. This would be where we would be at 2100 if we didn't take any action. This is a map from Climate Central. It factors in some new research about the state of Antarctica and what's going on with the melting there. And so this is, you know, my daughter will hopefully be alive to see this amount of warming and this amount of sea level rise. And obviously the scientists that are looking at sea level rise and lots of other impacts are pretty concerned. And some of them are thinking about what would be kind of emergency triage measures for the situation we're in. This is a cover story from The Economist last year called What They Don't Tell You About Climate Change. And so this is an issue that's been getting more press, is that the climate modeling scenarios used in the last integrated panel on climate change, intergovernmental panel on climate change report that came out a couple of years ago, are already assuming that we're doing something called negative emissions. They're assuming that we're going to figure out ways to suck carbon out of the atmosphere throughout this century, starting pretty soon, and that by the year 2100, we'll be removing about 10 billion tons per year. I'll talk a little bit more about what that means. But basically, the research being done by modelers assume that we're going to have these technologies to suck carbon out of the air, and that's how we limit warming to 2 degrees. However, these technologies are still conceptual or unproven at scale. And there's not too much political or economic will to build them. So now we're kind of in a bit of a bind. I'll talk briefly about this idea of a carbon budget. You might have heard of it. The idea is that we approach climate change with a certain amount we can emit until we reach that 2-degree mark. So keep in mind that the world has already warmed about 1 degree Celsius above pre-industrial. Here we are at 2018. This is our budget of 1,000 gigatons. That number is a bit contested, but it's a very rough estimate. Assume we have an account with 1,000 in it, and we're spending 40 to 50 per year. So 2019, we've spent that 40 or 50 gigatons of carbon dioxide. 2028, we've spent a significant portion more. By 2042, we've emitted enough to get us to the 2 degrees locked in. And then imagine, what if we're wrong about our calculation? We thought we had 1,000 gigatons to spend, but there was an accounting error, and we really only had 700. At that point, we're locking ourselves into 2 degrees much earlier at 2034. So these are pretty close-in timescales, is what I'm trying to convey. It's not so far off in the future. If you remember talking about this in the 90s and the 2000s, it probably felt pretty far off, but we're getting closer every year. And so this is a rather technical diagram, but I want to walk us through it because it's really actually the easiest way to explain what these scenarios are, believe it or not. So we've been emitting all this carbon. It's risen sharply, and a lot of it has actually just been since the 80s, 90s, 2000s. Got up to about this point. The pledges made under the Paris Agreement would kind of start to bend it down a little bit, but it's still actually increasing. This black line is the trajectory that a 2 degrees scenario would be. It shows us kind of really sharply dropping emissions right about now. This would be the peak, right? And then it goes down dramatically. To this point here, I want to point out, is where it crosses the 0 line. So that's like 0 emissions, somewhere in the 2070s. And then it continues to go negative. This is kind of net negative territory where we'd be removing these 10 gigatons of carbon every year. So this would be really difficult to do, but that's what we would need to do to keep warming to what the world agreed on is a safe level. And another thing to point out about it is that these negative emissions, to get there, we actually start producing them up here in the next decade or two. Part of the idea about this negative emissions is that some sectors are really difficult to mitigate, like aviation, that you've probably heard of. So to compensate for ongoing emissions in aviation or heavy industry, there would be other sectors, particularly the power sector, that are removing carbon from the atmosphere. So how do you actually remove carbon from the atmosphere? 2 big ideas I'm going to highlight first. One is direct air capture. So building out machines that extract carbon dioxide from the air using chemicals. This is a prototype in Switzerland, one of the first pilot plants. It's actually capturing the carbon and feeding it to greenhouses, not putting it underground. This is a visualization by some folks at Arizona State on what it might look like if you scaled these up over large areas of land. Technically possible, rather expensive at present. Some analysts think that the costs will go down as the technology matures. But there's a very large energy cost to doing this. So if you're going to remove this 10 gigatons, I'll just go back here. This is kind of what I'm going to keep referring to as this 10 gigaton by the end of century goal. It would require a huge amount, 1.5 times the wind and solar capacity already being used in a low carbon scenario, or about 1,200 nuclear power plants. Just some rough estimates of the scale of energy. And you'd want to be using that energy if you had that capacity for probably a lot of other things. So that's one big idea that's on the horizon, possibly. Another one is bioenergy with carbon capture and storage, something called BECCS. So this is what they put into these models because it's something that the technology exists to do it today. The idea is that you grow biomass, kind of like the biofuels we already have, and use trees or grasses, switchgrass, et cetera, crop residues. You put it into a power plant, you take out the CO2. You have the biofuels to use for heating and electricity and driving, perhaps. And the carbon dioxide gets piped elsewhere and stored underground. So one of the really difficult parts with scaling up this concept is the land demands for the bioenergy. So for that scenario I was talking about, for 2 degrees, you would need cropland of about the size of India to use for those biofuels. So that's why a lot of analysts are not very hopeful about scaling up this particular idea. But it's already in these kind of simulations about how we get to 2 degrees. Another idea that's come up, this is a lot more in the exploratory stages, but I want to mention it because here we are at the aquarium. In this aerial photo, this is offshore of Korea. These are actually seaweed farms. And the idea is that the bioenergy with CCS I just talked about has these extreme demands for land and water and fertilizer. What if we could get the bioenergy by growing crops offshore and growing seaweed offshore and using that with carbon capture and storage? There's a few companies, I pulled this from Marine Bioenergy, that are looking at, could we use kelp for fuel? This idea was proposed in the 1970s by Dr. Wilcox. There are some engineering challenges with it then, but now there's a prototype of robotic farms that could take the kelp down and bring it up to get sunlight. Something that I think is worth looking into more. Again, would require a lot. And these things are underpinned by carbon capture and storage technology. So roughly you'd need about 1,000 facilities of injecting carbon underground per the gigaton of CO2. So if you're going to draw down this 10 gigatons by the end of the century, you'd need to build 10,000 plants. We have about 15, maybe 20 in operation today. Just a handful that are capturing carbon from power plants and injecting it underground. You need a network kind of like this, maybe larger, for pipelines that are transporting it from power plants and other sources to the injection wells. I'd be more than happy to talk more about that. But my main point is just that the scale of this infrastructure is something on the order of the scale of the fossil fuel infrastructure we have already today. It would be building out kind of all of that again, except for putting the carbon back underground instead of taking it out and burning it. So this is a really epic kind of assumption that's already in these ideas about how we limit warming to 2 degrees, which is a really tough spot to be in, frankly. I put this in because it's a depiction about storing carbon under the oceans. I don't think this is the best way to go about it, but there are different conceptions of, could you put the CO2 into the oceans? There's already seabed geological storage offshore in Norway. In some ways, this is attractive because it avoids this issue of the not in my backyard thing, where people don't necessarily want to live on top of a bunch of carbon. So the ocean is out of sight, out of mind, right? I won't talk too much about that, but I will mention that there are other ideas about how to remove carbon. You'll often see these kind of diagrams. This one, actually, on the left is from Nature. This one's from Science. So in top journals, these are how they try to explain, but they say something like, take your pick, as if there's a menu, right? So We talked about the direct air capture a little bit. We talked about the bioenergy with carbon capture and storage. You can, of course, plant more trees. We know that trees take carbon out of the atmosphere. Blue carbon, so restore wetlands that can take in carbon. I guess the main thing I want to say about these is that we would need a combination of methods, but it gets a little bit tricky because some of these methods compete with each other in different ways. I wanted to mention a little bit more about blue carbon being in the aquarium. So there's coastal blue carbon methods, particularly mangroves, seagrass meadows, salt marsh habitat. It's being degraded at an incredible rate, and it stores a lot of carbon, and we could restore it and hold more carbon in there. There's all kinds of different types of blue carbon methods in the open oceans as well, away from the coasts. I could talk about that more later if you guys are interested, but one issue with these biological methods, like planting trees or storing carbon in soil, is that you do them one time, and then you plant your forest on this piece of land, or you start farming in a way that sequesters carbon in the soil on this piece of land. And then you have to hold it there for a very long, indefinite amount of time, or you lose that again, and it goes back into the atmosphere. Whereas something with like the bioenergy with CCS or the direct air capture, you put those machines on the ground, and then you keep them running, and they remove carbon year after year after year. So in that lens, they have more potential than afforestation or soil carbon, which are really great things we should be doing immediately. But so as I mentioned, the rollout of these carbon removal technologies would have to be very massive and also pretty quick, because in order to get to this net negative territory by the end of the century, we need to start building out that infrastructure, scaling up these techniques, figuring out which ones work well and under which contexts right about now. And every year of delay on stopping the emissions counts for a lot. So we can't just assume that we'll be able to kind of fix it all with removing carbon later in the future, just because of the difficulty of these methods. So imagine you spent $1 trillion over 50 years planting immense forests and convincing farmers that they should be farming in this really different way than what they know. That would take a lot of work. And all of it would only buy us 5 more years of our current rate of emissions. So actually stopping the emissions right now is the most important thing we can do. But then after that, suppose we did stop emissions, is there more we could do to repair / restore / make things better later on for our children and their children and their children? Is climate change reversible? No, not exactly, but there are some impacts that could be reversed or lessened. Some are clearly not reversible. So if a species goes extinct, then that's it. Other things like the frequency and intensity of storms that may be driven by surface temperature changes. If we bring those surface temperatures back down, then that could get better. So there's a lot of different terminology for climate engineering or geoengineering or climate intervention, as these National Academy reports put it. Basically, they all refer to technologies that would cool the Earth, either removing carbon or reflecting sunlight, that are both intentional and global at scale. And a little bit about the history of this concept. The methods that would reflect incoming sunlight in particular kind of came to attention in 2006 when the Nobel Prize winning scientist Paul Crutzen published this article, which it was actually a commentary in climatic change. Albedo enhancement by stratospheric sulfur injections, a contribution to resolve a policy dilemma. So he saw this really as a policy dilemma, and wanted to kind of be radical and propose, what if we put sulfur into the stratosphere? What effect would that have? And if you actually read his piece, he didn't think we would go about it because it doesn't fix the ocean acidification problem, which is something I'll talk more about in a minute. In 2009, this report got a lot of attention and laid out kind of different techniques for intervening in the climate system along these axes of safety and effectiveness and affordability and timeliness. And this is kind of how people thought about the concept of geoengineering for the next decade or so. One idea that's been discussed a lot more recently is just putting it in the context of carbon removal would take a lot of time to be implemented. This is where we are with business as usual. We would cut emissions aggressively, we hope, and then to bend down the impacts, remove carbon. And so some researchers are looking into whether solar geoengineering or reflecting incoming sunlight could buy time to scale up carbon removal and kind of lessen some of the impacts until we get to a point where we're removing carbon. So this is a question. Climate modelers are working on whether this is feasible, what it would look like, what kind of impacts it would have. The basic idea is that clouds and light-colored surfaces and particles in the atmosphere can reflect light back into space. So how would we go about making more light reflected back into space? That we know that would cool things down. We could increase the amount of clouds and their reflectivity. We could put reflective particles in the atmosphere. Notably, aerosol pollution just from cars and trucks and factories is already masking half a degree up to 1.1 degrees of warming, which is a really scary thing because if we cleaned up all the air pollution like we're trying to do, we would get that level of warming back. And so scientists, some of the earliest people working on this idea were inspired by studying volcanoes. We know that volcanoes can cause cooling by putting particles in the stratosphere because it's been observed. For example, Mount Pinatubo, when it erupted in 1991, resulted in a global cooling of 0.5 degrees and had other important climate impacts like reducing the monsoonal rains. But so that's kind of the thing scientists were studying and thinking about. Could we mimic a volcano by putting the particles up there ourselves? Could we do it on purpose? And so a few key points about this idea. The stratosphere is a layer above where weather happens and above where planes normally fly. And so if you put particles up there, they would stay for 1 to 2 years, circulate around the whole globe, and then come back to Earth. And because the particles are placed so high up, the health effects would be less dramatic than the health effects from the sulfur pollution that we're breathing in right now, because they have a longer time where they stay up there, so you don't need as much of them. How would you get the particles up there? This is a balloon system some scientists in the UK were thinking about testing out, and they actually decided not to do that test, actually, for interesting reasons involving controversies over patents and concerned citizens. They responded to that and decided, it wasn't appropriate to test this device for putting the particles up there. It's a very contentious field of research, obviously. You could also more feasibly put particles there with planes that are engineered to fly at those altitudes. So what kind of particles are we talking about? I mentioned sulfur dioxide. I snapped this picture of some sulfur a couple miles from here last time I was visiting the aquarium. That would have negative ozone implications, probably. So scientists are studying whether calcite, another mineral, might be better. And where would you put these particles? If you put them into the tropical latitudes, they would cool the planet globally. There's some discussion about whether injecting them further north would cool the Arctic more than other regions. Crucially, this does not return us to a climate we had before. It's just that in models, if you compare it to a worst-case climate change scenario, it does look better in some respects. It's all about what scenario you're comparing it to. There's a lot of potential negative impacts. I'll mention them. I don't want to be rushing through them, but there's a lot of other things to talk about, so feel free to flag these as questions later too. Damage to the ozone layer, interference with precipitation patterns. Some of this is really hard to predict too. Importantly, ocean acidification continues because the carbon is still here. It hasn't been removed by this method of reflecting the incoming sunlight. The skies would be a little bit whiter because of the way the light would reflect through the particles. And there's a lot of ecosystem unknowns because you're changing the amount and type of light coming down to Earth. So that's something that could be really drastic for all of us that use light. Another really troublesome thing about this method is that if you suddenly stopped the solar geoengineering, putting the particles up there, if some catastrophe happened, like a world war or something that made it impossible to continue, the warming that you'd been suppressing would happen all at once. And so you might have been suppressing, several decades worth of warming with this solar radiation management. You brought temperatures back down, but then all of a sudden the intervention gets interrupted, and your temperatures are going to shoot back up in the matter of a few years, which would be something that species can't adapt to such a rapid rate of warming. Now, some people think that, that's not a very likely scenario because the society that had chosen to start putting these particles in there would obviously choose to keep doing it. But people who are concerned about this prospect really want to highlight this possible scenario. So there you have it, another version of this diagram. Could you buy time for carbon removal with solar geoengineering? One thing I wanted to talk a little bit about is this prospect of whether geoengineering could help ocean life. Carbon removal is not a true remedy for ocean acidification because of how ocean water circulates. So if you removed carbon from the atmosphere, you could remove carbon from the surface layers of the ocean, but it would still be in the deep ocean for a very long time. However, there's two interesting ideas that have been discussed. One is this question of whether silicate or carbon minerals could be added to ocean waters to make them more alkaline. So places that are locally suffering from ocean acidification, could you add minerals to that water to reduce that? Another idea is, can marine clouds be created to reduce local temperatures, say on the Great Barrier Reef or some other habitat we really care about? In terms of enhancing alkalinity, this is olivine, something that's been discussed in terms of adding it to the waters. This is a diagram of different ways you could do it. You'd have to extract these minerals, kind of grind them up and add them either to cropland. So that's one thing that's been proposed and being tested, particularly with basalt, is you would grind up basalt, spread it over crops. It fertilizes the crops and also sequesters carbon because it speeds up this natural reaction of weathering. I won't talk about that too much because it's getting into the weeds. But anyway, adding it to the ocean waters is something that's being researched a little bit. This is a new paper that came out this week, so I didn't have time to really digest it, but I put it up there in case somebody really wants to look into it. It's a proposition for how to merge renewable electricity, saline water electrolysis, and enhanced mineral weathering to produce a hydrogen fuel and at the same time alkalize seawater. So brightening marine clouds is another idea that is garnering a little bit of research, although I want to say that this is a field that doesn't have a lot of research funding. Maybe I'll back up and talk about that for a minute, because I think it's important to understand. I don't want to present all these things like there's like thousands of people energetically working on them. I'm really talking about maybe 100 people globally who are spending their day-to-day researching these things and producing a fair amount of papers, actually. But in terms of big research programs, the United Kingdom has a program on greenhouse gas removal that they have on the order of maybe tens of millions of dollars, pounds, obviously. There's a research program in China. There's research efforts in Germany, mainly focused on assessing the risks of these things. And there's not very much federal research funding in the US for these types of ideas. But there's people that work on it anyway because they're really concerned about it, right? So some of the marine cloud brightening people fall into that category. And they're thinking about, could you use special ships, like this artist's rendering, to inject salt from seawater into the air to create clouds, or ships or platforms or some other, spraying technology. This isn't necessarily high, fancy technology. It's creating clouds with stuff that's on hand. But ship tracks have a similar effect where they create clouds. So that could potentially cool the area, say, around a reef that could really benefit from that. That's, I guess the main points I want to highlight are that some climate change impacts like deep ocean acidification, species loss, or ice sheet loss are difficult or impossible to reverse. But there is a window of opportunity for reversing some other changes. This research and effort would need to happen on top of cutting carbon emissions. It's decarbonization and then a step further. So it's not a substitute for the work we need to do with mitigation. It's actually an even more ambitious add-on to that, is how I see it. And so I really do think that during this decade, we have a chance to put ourselves on a path to make the climate less extreme and more livable for future generations. I've talked about a lot of very depressing things, but I don't actually feel totally depressed about the situation because I talk to everyday people who are innovating new technologies or new approaches or working with community groups that are working on soil carbon, and there's so many different ideas bubbling up right now that more and more people are realizing that we're kind of at a crisis point, and they're thinking of things that we could do. If a few more minutes, I could talk about a couple of things. One of them would be kind of what people are thinking about these technologies and how they've responded to them. There have been about 30 studies about what people think about climate engineering when they hear about it. Most of them have been smaller studies. There's been a few surveys where they go out and just read people a question, tell them a little bit about this technology and say, what do you think? Do you think we should be spending our money and time on this? There's a few workshops where they go in depth into people. I'll skip that one. And so they're looking at, what factors are driving people's perceptions of this. Do they feel excited or hopeful that we're going to fix climate change? Generally, no. People are generally really cautious, and we think first about the really awful, unexpected side effects that could happen, right? I won't talk too much about this, but the findings have been a little bit interesting in that across different countries, even ones that have different cultures of how they think about nature, people have very similar concerns. So people are wondering about kind of ecological impacts. They think about things like what happened when the cane toads were introduced to Australia and they got out of hand, or what happened when we invented plastics and chemicals. We thought they were going to be so great, and then, you know, these things happened and now the oceans are full of plastic and nobody wanted that to happen, but here we are. One interesting finding that hasn't been found in every study, but in a few, is that when people are given information about geoengineering, they tend to take climate change more seriously. So that's one thing being investigated a lot right now. And then there's a big discussion on whether people from other countries, like developing countries that are really on the front lines of climate change, are they going to be more cautious about this because they have such history of people in the global north changing the environment and they just feeling like they're responding to it? Or are they going to want to take a lead and look at this further because it could be an existential solution if you're a small island state, for example? I think I probably will back up and leave it there because I'm really curious to have a discussion with all of you and answer your questions.